Hello and welcome to the 8D Sleep Lab. Before we begin, please take a moment to click the like button. It helps other sleepy minds find this quiet space in the algorithm. This session utilizes bilateral 8D audio. For the full hypnotic effect of the sound moving around you, headphones are recommended. Now, let go of the day. Unclench your jaw, drop your shoulders, and let your hands rest loosely by your sides. Tonight, we are not looking for excitement. We are looking for viscosity. We will observe the slow thermal transition of solid sand into liquid glass. There is no plot. Just the heat and the flow washing over you from ear to ear. Let us begin. Chapter 1. The Batch House, Raw Materials. We begin our journey not at the fire, but at the dust. Welcome to the Batch House. It is a tall, concrete structure, standing separate from the main furnace hall. Here, the air is still. There is a low, rhythmic hum of ventilation fans, filtering the dry, suspended particulate matter from the atmosphere. This is the place of recipe, the place of precision, before glass becomes transparent, before it becomes a vessel or a window or a lens. It is merely a collection of geological powders. We call this mixture the batch. To create standard, commercial, Soda-Lime-Silicate glass, we must follow a strict chemical architecture. It is not enough to mix things together. We must weigh them to the kilogram, to the gram, to the decimal point. Let us look at the first and most abundant ingredient, silica, silicon dioxide, SiO2. This creates the network, the backbone of the glass structure. In our recipe, silica makes up exactly 72%. 72%. Imagine a silo, a vertical steel cylinder rising 60 feet into the air. Inside this silo sits 300 tons of high purity quartz sand. It is not beach sand. Beach sand is too uneven, too contaminated with shells and debris. This is industrial silica sand. It is white, pale, uniform. The grains are subangular. They are not perfectly round, nor are they sharp. They are sized between 0.1 and 0.5 millimeters. We require this specific size because if the grains are too large, they will not melt completely. They will survive the furnace as stones, small, white inclusions that ruin the glass. If the grains are too small, like dust, they will be carried away by the draft of the furnace flames. They will clog the regenerators. So we wait as the automatic feeder opens at the bottom of the silo. Gravity pulls the sand down. The sand falls onto a rubber belt scale, a steady, heavy stream. We watch the digital counter rise. 100 kilograms, 500 kilograms, 720, kilograms for every metric ton of glass. 72%. The sand is chemically stable. It provides the glass with its hardness, its durability, its resistance to weather, but silica on its own has a problem. It has a melting point of 1,710 degrees Celsius. 1710. This is too hot. It consumes too much energy to melt pure sand. We need a flux. We need a chemical agent to attack the silica, to break its bonds, and lower the melting temperature. This brings us to the second ingredient, sodium oxide, Na2O. We derive this from soda ash, sodium carbonate, in our badge. This accounts for 13%, 13%. The soda ash sits in the second silo. It is a fine white powder, much finer than the sand. It feels soft, almost slippery to the touch. It is soluble in water. It is light. When the feeder opens, the soda ash flows like water. It creates a small cloud of white dust as it hits the weighing belt. 13%. The role of the soda ash is strictly thermal. It is a fluxing agent. When mixed with the silica sand and heated, the sodium ions insinuate themselves into the silicon network. They disrupt the rigid crystal structure. They effectively loosen the lattice. This lowers the melting point from 1700 degrees down to a manageable 1500 degrees. But there is a cost. Sodium is soluble. If we made glass from only sand and soda ash, it would be called water glass. Sodium silicate. It would look like glass. But if you poured water into it, the glass would eventually dissolve. It would melt away into a sticky, gelatinous liquid. This is not useful for a bottle or a window, so we must add a stabilizer. We must make the glass insoluble. This brings us to the third ingredient, calcium oxide, CaO, commonly known as lime or limestone, calcium carbonate. In our recipe, this accounts for 10%, 10%. The limestone sits in the third silo. It is a heavier powder. It is dull grey or off-white, depending on the quarry source. It is essentially ancient, crushed rock. The calcium ions enter the glass structure and block the pathways that water molecules would otherwise use to attack the glass. The lime makes the glass strong. It makes it chemically durable. It ensures that the glass will last for thousands of years. 10%. We watch the scale. 100 kilograms of limestone dust settling onto the belt, layered on top of the soda ash, layered on top of the sand, a sandwich of minerals. And now, the fourth ingredient, magnesium oxide, MgO. This makes up 4% 0.4%. Usually we introduce this along with the lime in the form of dolomite. Calcium magnesium carbonate. The magnesium acts as a secondary stabilizer. It prevents the glass from devitrifying. Devitrification is the enemy of the glassmaker. It is when the glass tries to return to a crystalline state. If glass devitrifies, it becomes milky, opaque, rough. The magnesium atoms help keep the mixture amorphous. They ensure that the liquid freezes as a clear, solid liquid. 4%. We have our primary recipe: 72% silica, 13% soda, 10% lime, 4% magnesia. That equals 99%. The remaining 1% consists of minor additives: alumina, aluminum oxide to improve, viscosity, iron oxide to provide a slight green tint or to be removed for clear glass, and fining agents like sodium sulfate, salt cake. These are added in mere grams, a handful of powder into a mountain of sand. But we are not finished with the batch house. We have one more component, the most crucial component for the modern furnace: cullet. C-U-L-L-E-T. Cullet is simply broken glass, recycled glass. It sits in its own massive concrete bunker. There are two types of cullet. First, there is internal cullet. This is glass that never left the factory. Bottles rejected for being too heavy. Jars rejected for having a bubble. The trim cut off the edges of window sheets. This glass is crushed into pieces the size of a coin. It is perfectly clean. We know exactly what is in it because we made it. Then there is external cullet, foreign cullet. This comes from the recycling centers, from the bottle banks, from the blue bins. It arrives in dump trucks. It must be cleaned, processed. Magnets remove the metal caps. Eddy currents remove the aluminum foil. Lasers detect and remove ceramics and stones. Why do we add broken glass to the batch? Why not use fresh raw materials? Thermodynamics. Cullet has already been melted. The chemical reaction is already complete. The sand and the soda have already reacted. To melt cullet requires 30% less energy than to melt raw batch. For every 10% of cullet we add, the furnace temperature can be lowered or the output can be increased. So we add cullet, lots of it. In a modern furnace, the ratio might be 40% cullet, 50%, sometimes up to 80%. Listen to the sound of the cullet dosing system. It is a harsh, clattering sound, like gravel pouring down a chute. The shards of glass slide out of the hopper. They fall The cool, quiet dust of the batch house behind. We follow the belt. We follow the sand. We follow the cullet, moving slowly, 1 meter per second, towards the doghouse, towards the melter, towards the transformation. Chapter 2. The Regenerative Tank Furnace. We leave the cool air of the conveyor belt. We step into the furnace hall. The environment here changes instantly. The temperature rises to 40 degrees Celsius, 50 degrees. The sound is a continuous, oppressive roar. It is not a mechanical noise. It is the sound of high-velocity combustion. Standing before us is the tank. It does not look like a tank. It looks like a fortress, a massive rectangular block of refractory brick, 10 meters wide, 20 meters long, held together by a skeleton of heavy steel buckstays, compressed by massive tension rods. This brick box glows. Heat leaks from every seam, from every peephole. This is the melter, the heart of the factory. It holds 400 tons of molten liquid, 400 tons of lava. We begin at the doghouse. This is the feeding port. It is a small, open vestibule at the rear of the furnace. The conveyor belt above releases the grey batch mixture that we prepared in the batch house. It falls into the charging machine. A large metal pusher oscillates back and forth, slowly. It pushes the pile of powder gently into the furnace. We call this pile the blanket. It floats. The raw materials are lighter than the molten glass, so the grey powder floats on top of the orange liquid like an iceberg. As the pusher extends, it sends a fresh raft of powder drifting into the inferno. The blanket moves forward, drifting slowly towards the center of the tank. As it moves, it begins to vanish. The underside of the blanket is licking the molten glass. The heat transfers from liquid to solid. The sand grains dissolve. The soda ash melts. The gray pile shrinks. It turns wet, then glossy, then it is gone, subsumed into the bath. Inside the tank, the temperature is 1,575 degrees Celsius. This temperature must be maintained precisely. If it drops, the glass becomes too thick. If it rises, the refractory brick of the furnace walls will begin to melt along with the glass. To achieve this heat, we use fire, natural gas burners, but fire alone is not enough. If we simply burned gas with cold air, we could never reach 1,500 degrees efficiently. We need regeneration. We need to recycle the heat. This Let us observe the cycle. The furnace breathes. For 20 minutes, the fire flows from left to right. Gas enters through the ports on the left side. It mixes with preheated air. It ignites. A massive sheet of flame sweeps across the surface of the glass. It licks the batch blanket. It transfers its energy into the melt. The exhaust gases now spent exit through the ports on the right side. But the exhaust is still hot, very hot. It flows down into the right regenerator. It passes through the checker bricks. The bricks absorb the heat. They glow bright yellow. They store the energy. The waste gas becomes cooler as it descends. By the time it reaches the chimney, the heat has been trapped in the bricks. Then the cycle ends, the reversal. A siren sounds. A mechanical valve shifts. The gas flow stops. For 3 seconds there is silence in the furnace. The flame dies. The roar pauses. Then the airflow reverses. Cold air is pumped into the bottom of the right regenerator. The air rises up through the hot checker bricks. It steals the heat back. The bricks cool down. The air heats up. By the time the air reaches the top, it is already 1,200 degrees. It meets the gas nozzle. Ignition. The flame now roars from right to left, sweeping back across the glass. Now the exhaust exits on the left, heating up the left regenerator, charging the battery once again, left to right, right to left, every 20 minutes, 24 hours a day, for 12 years. The furnace never stops breathing. If the reversal valve fails, the furnace dies. We look back at the liquid. The glass is now melted, but it is not ready. It is full of gas. Chemical reactions release carbon dioxide. Trapped air creates bubbles, thousands of tiny bubbles. We call these seeds, and large bubbles, called blisters. If we formed a bottle now, it would look like champagne. Weak, defective. We must move to the fining zone, the hot spot. This is the hottest part of the tank. Here, the flow of the glass slows down. We add sodium sulfate, the fining agent. At this precise temperature, the sulfate decomposes. It releases sulfur dioxide gas, SO2. This gas forms large bubbles. These large bubbles rise quickly. Stokes' law: the velocity of a rising sphere is proportional to the square of its radius. The large sulfate bubbles sweep upward. As they rise, they collide with the tiny seeds. They absorb them like a vacuum cleaner, collecting the defects and carrying them to the surface, where they pop, bursting into the furnace atmosphere, leaving the glass below pristine, clear, homogeneous. The glass has now traveled halfway down the tank. It is refined but it is still too hot. It is as thin as water. We cannot shape it yet. It must be conditioned. It approaches the throat. The melter ends at a wall, a bridge wall. The glass cannot go over the wall. It must go under. There is a small tunnel, submerged deep, at the bottom of the tank. The throat, only the purest, heaviest glass, sinks to the bottom. The scum, the unmelted stones, float on top and are blocked by the wall. The good glass flows silently through the submerged tunnel. It passes from the melter to the working end, also known as the forehearth. Here, there is no fire, no turbulence, just a quiet, cooling pool. The glass temperature drops from 1500 down to 1200. Its viscosity increases. It turns from water into honey. It flows slowly through narrow channels, waiting for the shears, waiting to be cut. Chapter 3. The Tin Bath, the Float Process. We have melted the raw earth. We have refined the bubbles. We have cooled the lava into a thick, viscous honey. Now we must make it flat, perfectly flat. For centuries, this was impossible. Glass was blown, spun, rolled, but it was never flat. It always had distortions, waves, imperfections, until the float process. We approach the canal, a narrow ceramic lip. The glass flows over this lip, like a waterfall in slow motion. It descends gently and lands onto a liquid lake. But this is not a lake of water. Water would boil instantly. It is not a lake of oil. Oil would burn instantly. This is a lake of molten tin. Element number 50, SN, stannum. The bath is massive, 50 meters long, 8 meters wide, contained within a gas-tight steel casing. Inside holds 200 tons of pure liquid metal. Why tin? Why this specific element? Because it possesses a unique thermal window. We need a liquid that remains fluid at 600 degrees, but does not boil at 1000 degrees. Lead is too toxic. Gallium is too expensive. Aluminum melts too high. Tin is perfect. It melts at a low 232 degrees Celsius, but it does not boil until 2600 degrees. It stays liquid. It stays calm. It stays flat. Gravity. Gravity is the only tool we use. Because the tin is liquid, gravity pulls its surface into a perfect horizontal plane, a mirror. The glass pours onto this mirror. Glass has a density of 2.5 grams per cubic centimeter. Tin has a density of 7.3 grams per cubic centimeter. The tin is 3 times heavier, so the glass does not sink. It floats, just as oil floats on water. The ribbon of glass floats on the river of tin. The contact point, where the glass meets the metal, the temperature is 1050 degrees. The glass is soft. It surrenders to gravity. It spreads out, left and right, unhindered. It spreads until it reaches equilibrium thickness. If we touch nothing, if we let physics take its course, the glass will naturally spread to a thickness of exactly 6 millimeters. This is determined by the surface tension between the glass and the tin. But there is a danger. Tin loves oxygen. At these temperatures, if the liquid tin touches the air, it will oxidize immediately. SnO2, tin oxide. This oxide forms a skin, a crust. We call it dross. If dross forms, it will stick to the bottom of the glass. It will create scratches, haze, a defect called bloom. To prevent this, we must banish the air. The entire tin bath is a sealed vessel. Inside, we pump a specific cocktail of gases: 96% nitrogen, 4% hydrogen. This is called a reducing atmosphere. The nitrogen, N2, is inert. It creates a blanket of pressure. It keeps the oxygen out. The hydrogen, H2, is the scavenger. If any rogue oxygen atom manages to sneak in, the hydrogen finds it. It binds with it, H2 plus O. It creates water vapor, which is vented away. The hydrogen scrubs the tin. It keeps the metal pure, silver, shiny. We move further down the bath. The glass ribbon is moving forward, but we do not always want 6 millimeter glass. Sometimes we need thin glass. For smartphone screens, for car windows, sometimes we need thick glass. For shop fronts, for tables. How do we change the thickness without touching the surface? We use top rollers. Looking through the peepholes along the side of the bath, we see them. Long steel arms extending into the heat. At the end of each arm is a toothed wheel, the knurl. These wheels bite into the very edge of the glass ribbon, just the outer 2 centimeters, the selvage edge. If we want thin glass, we angle the rollers outward and we speed them up. They pull the glass, they stretch it, widthwise and lengthwise, like stretching pizza dough. The glass thins down 5 millimeters, 4 millimeters, 3 millimeters. If we want thick glass, we reverse the angle. We push the glass inward. We compress it. We dam the flow. We reach the end of the bath, the cold end, although it is not cold. The temperature has dropped to 600 degrees. The glass is now hard. It is no longer a liquid. It is a rigid, solid sheet. It must leave the tin. This is a critical moment. The lift out. 3 stainless steel rollers, lift out rollers. They rotate slightly faster than the bath speed. They gently peel the glass off the liquid metal. The glass rises. It hangs in the air for a brief second before touching the rollers. We must be careful here. If the glass is too hot, the rollers will leave marks, indentations. If the glass is too cold, it might crack from the thermal shock. 600 degrees, the perfect point. Behind it, the liquid tin flows back under the ribbon, recycling itself within the bath. The glass moves on, leaving the sealed atmosphere, leaving the nitrogen, leaving the hydrogen. It enters the tunnel, the annealing layer, where the final cooling begins. Chapter 4: Viscosity and Thickness Control. We are now floating in the middle of the tin bath. The glass ribbon is a continuous river, but it is a river that is slowly forgetting how to flow. We must talk about viscosity. Viscosity is the internal friction of a fluid. It is the measure of resistance to gradual deformation by shear stress. In the world of glassmaking, we do not use seconds. We do not use meters. We use the poise, named after Jean-Léonard Marie Poiseuille. It is the standard centimeter gram second unit. 1 poise equals 1 dyne second per square centimeter, or 0.1 Pascal seconds. Water at 20 degrees Celsius has a viscosity of 0.01 poise. Olive oil is 0.8 poise. Honey is 20 poise. Molten glass inside the furnace was 100 poise, but here on the bath the numbers rise exponentially. Glass viscosity is logarithmic. As the temperature drops by just a few degrees, the stiffness multiplies by 10. We map the journey of the glass, not by distance, but by these fixed viscosity reference points. First, the working point, temperature 1030 degrees Celsius, viscosity 10 to the power of 4, poise 10,000 poise. This is the consistency of thick, cold molasses. At this stage, the glass is pliable. It can be stretched, it can be bent, but it is strong enough to hold its shape against gravity for a moment. This is where we determine the thickness. Left to its own devices, nature has a preference. If we simply poured the glass onto the tin and touched nothing, gravity would pull it down. Surface tension would pull it in. The two forces would fight. and they would agree on a compromise. Equilibrium thickness for soda-lime-silicate glass floating on tin. This magic number is roughly 6 millimeters, or slightly more precisely, 0.23 inches. If we poured a puddle the size of a swimming pool, it would settle at 6 millimeters deep. If we poured a drop the size of a coin, it would flatten to 6 millimeters. But the world does not always want 6 millimeter glass. The architect designing a skyscraper demands 19 millimeters to resist the wind. The automotive engineer designing a windshield demands 2.1 millimeters to reduce weight. We cannot change physics, but we can manipulate it. We use the top rollers. Look through the side window of the bath casing. You see a row of steel shafts. They enter the chamber horizontally. They hover just inches above the molten tin. These shafts are water-cooled. Inside the steel pipe, cold water circulates constantly. Without this internal river of water, the steel shafts would glow red. They would soften. They would bend. At the end of each shaft is a wheel. The knurl. It looks like a gear. It has sharp metal teeth. These teeth bite down. They bite into the very edge of the floating glass ribbon, the selvage edge. This outer inch of glass is sacrificial. It will never be used. It is there, only to be gripped. We use these machines to override the equilibrium. Mode 1. Attenuation. This is how we make thin glass. We engage 10 pairs of top rollers, 10 on the left, 10 on the right. We angle the shafts slightly outward, pointing away from the center line, and we increase the speed. The rollers spin faster than the flow of the glass. They grab the edge. They pull. They exert a lateral tractive force. The glass ribbon widens. It stretches. As the width increases, the thickness must decrease. Conservation of volume. 6 millimeters becomes 5. 5 becomes 4. 4 becomes 3. We must be careful. If we pull too hard, the ribbon will snap. It will break like a rubber band. If we pull too unevenly, we create optical distortion. The speed of every roller must be synchronized to the decimal point. Mode 2. Directing. This is how we make heavy glass, thick glass. We reverse the operation. We angle the rollers inward, pointing towards the center line, and we slow them down. The rollers spin slower than the flow of the glass. They act as a brake. They act as a dam. The liquid glass flowing from the furnace hits this resistance. It has nowhere to go. It piles up. It swells. The ribbon narrows. The thickness rises. 10 millimeters, 12 millimeters, 15 millimeters, 19 millimeters. We are forcing the glass to defy gravity. We are forcing it to stand taller than it wants to. This requires immense control. The viscosity must be high enough to hold this thickness. If the glass is too hot, it will simply slump back down. The moment it leaves the rollers, it will flow back to 6 millimeters. This brings us to the most critical number in the viscosity index, the Littleton softening point, standard test method, ASTM 338. This is defined as the temperature at which a uniform fiber of glass, 0.65 millimeters in diameter and 23.5 centimeters long, elongates under its own weight at a rate of 1 millimeter per minute. For our glass, this occurs at 720 degrees Celsius. The viscosity is 10 to the power of 7.6 poise. 40 million poise. This is the threshold. At this point, the glass is no longer a liquid, but it is not yet a solid. It is in the plastic state. It is easily deformed, like warm wax or stiff clay. We must pass through this temperature very carefully. If we touch the glass here with anything cold, it will freeze instantly. It will lock in the stress. As we move past the rollers, the glass continues to cool. 650 degrees, 600 degrees. The viscosity climbs vertical. 10 to the power of 9, 10 to the power of 10, 10 to the power of 11. We reach the annealing point. 550 degrees. 10 to the power of 13. Poise. 10 trillion. Poise. At this viscosity, the internal stress can be relieved in 15 minutes. If we go any colder, without relieving the stress, the glass will become a time bomb, waiting to shatter. Finally, the strain point, 500 degrees, 10 to the power of 14.5, poise, 3 quadrillion, poise. At this point, the glass is functionally solid. For all practical purposes, it moves like a rock. Fracture will occur before flow. The atoms are locked. The random amorphous network is frozen in time. The thickness, whatever we made it, is now permanent. The ribbon leaves the tin bath. It crosses the gap, the lift out. It is a hard, continuous, transparent board, moving at 15 meters per minute. But inside the glass, hidden deep within the atomic structure, there is tension, thermal unevenness. If we let it cool in the room air, it would explode. It would shatter into dust. We must heal the glass. We must treat it. We must enter the Lehr. Chapter 5. Chemical Vapor Deposition. This is not a painting process. We are not spraying liquid. onto the glass. Liquid would boil. It would shock the surface. We are using gas, vapor. We call this pyrolytic coating. Pyro, meaning fire. Lytic, meaning to separate. We are using the heat of the glass itself to rip molecules apart and fuse them to the surface. The result is a hard coat. The coating will not be on the glass. It will be of the glass, fused, covalent, permanent. Above the ribbon hangs the coater. It looks like a massive steel beam spanning the entire width of the glass flow. Inside this beam is a complex manifold, a system of slots. We pump in the precursors. These are organometallic chemicals, liquids that have been vaporized into a gas. The primary chemical for low emissivity glass is often monobutyltin trichloride, MBTC. We mix this vapor with oxygen and sometimes a doping agent, like hydrogen fluoride. The gas travels down the slot. It hits the glass. The glass is hot, 600 degrees. Thermal decomposition begins instantly. The molecule shatters. The carbon burns away. The hydrogen burns away. The chlorine bonds with hydrogen to form hydrochloric acid gas, which is vacuumed away. What is left? Tin and oxygen, SNO2. Tin dioxide. The tin atoms dive into the hot surface. They find the oxygen atoms in the glass structure. They bond. They crystallize. In a fraction of a second, a layer forms. It is a ceramic layer, transparent, conductive, but we cannot just apply one layer. If we apply tin oxide directly to soda-lime glass, we have a problem. Sodium. The sodium ions in the glass are restless. Over time, they will migrate out of the glass and into the coating. They will ruin the crystal structure. They will cause haze. So first, we must lay down a barrier layer, a primer, silicon dioxide. Silica, we use a precursor like silane, SiH4. The silan hits the glass first. It forms a microscopic shield, only 20 to 30 nanometers thick. This shield locks the sodium inside the glass. It provides a neutral foundation for the active layer. Now, the second beam activates. The tin oxide layer. It grows on top of the silica, crystal by crystal, columnar grain growth. We need a specific thickness. If the layer is too thin, it will not reflect heat. If the layer is too thick, it will create interference patterns, rainbows, oil slick colors. We do not want rainbows. We want neutrality. The target thickness is typically 300 to 400 nanometers. A nanometer is 1/1000th of a meter. A human hair is 80,000 nanometers wide. We are applying a coating that is 200 times thinner than a hair, and we are doing it onto a substrate moving at 15 meters per minute. and we must maintain this thickness across a width of 3.2 meters, with a variance of less than 2%. This requires laminar flow. The gas must not swirl. It must not be turbulent. It must flow like a smooth sheet. We adjust the exhaust vents. We balance the pressure, millibar by millibar. Why do we do this? Why go to such trouble for an invisible layer? Emissivity, epsilon. Standard glass has an emissivity of 0.84. This means it absorbs and radiates 84% of the heat energy that hits it. In the winter, your house is warm. The heat travels to the window. The glass absorbs the heat and radiates it outside. You are heating the garden. With our CVD coating, the tin oxide layer is conductive. It has free electrons. These electrons interact with infrared light, long-wave radiation. When the heat wave hits the coating, the electrons vibrate. They act like a mirror. They reflect the heat back into the room. The emissivity drops from 0.84 down to 0.15, only 15% heat loss. The glass is now a thermal barrier, but to the visible eye, looking at the sunset, it is still clear. Visible light has a shorter wavelength. It passes through the electron cloud undisturbed. Magic? No. Quantum mechanics. Band gap engineering. We monitor the haze. We monitor the sheet resistance, ohm per square. If the resistance is too high, we add more fluorine dopant. If the haze is too high, we adjust the precursor temperature. The vapors are toxic, corrosive. The entire beam is encased in negative pressure. Scrubbers clean the exhaust. The glass moves on. It carries its new armor. The coating is hard. You can scratch it with a key, and it will not flake. You can wash it with acid, and it will not dissolve. It has become the skin of the glass. The ribbon barely cools during this process. It is still 600 degrees. It is still plastic. It is still stressed. It must now face the final discipline, the controlled, slow cooling, the annealing layer. Chapter 6, the annealing layer. The glass has left the tin bath. It has been lifted over the threshold. It has survived the fire. It has survived the stretching. Now it must survive itself. We enter the Lehr, L-E-H-R. This is not a German word. It creates confusion, but in the glass industry, it means only one thing: the tunnel of time. The glass ribbon is now a solid sheet, 3.2 meters wide, moving at 15 meters per minute. It enters a long, insulated metal corridor, 100 meters long, to the outside observer. Nothing is happening. There are no flames. There are no chemical sprays. There is only the silent turning of rollers. hundreds of steel rollers, spaced every 30 centimeters, carrying the infinite sheet into the dark. Why do we need this tunnel? Why not just let the glass cool in the room air? The answer is stress. Glass is a poor conductor of heat. It is an insulator. If we expose hot glass to cool air, the surface cools instantly. It contracts. It tries to shrink, but the center of the glass, the core, is still hot. It is still expanded. The surface tries to squeeze the core. The core fights back. Tension, compression. If the temperature difference, the delta T between the surface and the core, exceeds 50 degrees, the glass will self-destruct. It will not just crack, it will detonate. So we must control the cooling. We must manipulate the atoms one last time. We enter Zone A, the heating zone. This seems counterintuitive. We are trying to cool the glass, so why are there electric heating elements in the roof? Because the glass arrived uneven. The edges touch the lift-out rollers. They are slightly cooler. The center is slightly hotter. Before we can cool down, we must equalize. We soak the glass. We hold the temperature at exactly 545 degrees Celsius. This is the annealing point. Viscosity 10 to the power of 13. Poise. At this precise temperature, the glass atoms are allowed to relax. Imagine a tangled knot. If you pull it tight, it stays knotted. If you wiggle it gently, it loosens. Heat is the wiggle. At 545 degrees, the stress relaxes in 15 minutes. We hold it here. The heating coils glow, a dull red. They gently radiate energy down onto the ribbon, ensuring that the left edge, the center, and the right edge are perfectly identical. 545, 545. No gradient, no tension, only peace. We move to Zone B, the slow cooling zone. This is the most critical section. We must lower the temperature, but we must do it so slowly that the glass does not realize it is cooling. We drop the temperature at a rate of 3 degrees per minute. 3 degrees. The sensors read 540, 537, 534. If we go too fast, we cross the strain point with a thermal gradient. The strain point, 500 degrees Celsius. This is the point of no return. Once the glass passes below 500 degrees, its structure is set forever. It becomes an elastic solid. If there is stress in the glass at 500 degrees, that stress becomes permanent. It becomes a frozen stress. It will be there when the glass is cut. It will be there when the glass is installed in a window. It will be there 10 years from now, waiting. So we cross the threshold, gently, tiptoeing, past the strain point. The heating elements turn off. The insulation thins out. We allow the heat to escape naturally. Through the roof dampers, the sensors read 490, 480. We are safe. The structure is locked. The atoms are frozen in a stress-free state. We move to Zone C, the fast cooling zone. Now we can accelerate. The glass is solid. It is strong. We can no longer create permanent stress. We can only create temporary stress. If we cool it fast, the glass will bow. It will bend, but it will not break if we stay within limits. We introduce air. Convection fans turn on. They blow room temperature air into the tunnel. It creates a counterflow. The air flows against the direction of the glass. This is turbulent heat transfer. The temperature drops rapidly. 400 degrees, 350 degrees, 300 degrees. Listen to the sound of the Lehr drive. It is a rhythmic, mechanical heartbeat. Clunk, 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 clunk. Each roller is chained to the next. A single motor drives the entire 100-meter train. Why? Because if one roller stopped while the others turned, the glass would scratch. The glass would pile up. So they turn in unison, perfectly synchronized, carrying the burden. We move to Zone D, the retardation cooling, 250 degrees, 200 degrees. At these temperatures, the glass is safe to touch for steel, but not for hands. It is essentially a hot stone highway. We check the flatness. If the top surface cools faster than the bottom surface, the glass will curl upward. We call this up bow. If the bottom cools faster, it curls downward, down bow. We want dead flat. So we adjust the bottom vents. We blow air up between the rollers, cooling the underside, balancing the sheet, keeping it planar. 150 degrees, 100 degrees. We are nearing the exit, the end of the tunnel. The light changes. Inside the Lehr, it was dark, dim, orange glow fading to black. Now we see daylight, or the artificial fluorescent light of the cold end. The ribbon emerges. It travels through the curtain, a rubber flap designed to keep the dust out and keep the heat in. The glass slides out. It is clear. It is solid. It is cool enough that water will not boil on it. 60 degrees Celsius. Warm to the touch, like a mug of coffee. But it is moving fast. 15 meters.
21 kilometers every day. We have created a continuous, endless sheet, but we cannot sell an endless sheet. We cannot ship infinity. We must find the defects, and we must make the cut. The laser scanners are waiting. The snapping bridges are waiting. But for now, the glass rests on the open conveyor, breathing, settling, finished with its journey through the fire, finished with its journey through time.
Chapter 7: The Cold End. We step through the curtain. We leave the tunnel. The air here is different. It is cool, conditioned, 22 degrees Celsius. The light is stark. Overhead, rows of high-intensity LED bars illuminate the ribbon. The glass is no longer a liquid. It is no longer a plastic sheet. It is a continuous transparent highway, moving at 15 meters per minute. It stretches out before us, endless, silent, but it is not alone. Standing over the ribbon, like sentinels, are the scanners, the automated, optical, inspection system. The human eye is not good enough. The human eye blinks. The human eye gets tired. The laser never blinks. We approach the floor scanner. It is a massive beam, spanning the full width of the glass. Inside, a mirror polygon spins 30,000 revolutions per minute. It fires a laser beam, a helium neon laser, red light. The spinning mirror sweeps this beam across the moving glass, left to right, left to right, thousands of times a second. The beam passes through the glass. Underneath the ribbon is a receiver, a photomultiplier tube. If the glass is perfect, the light hits the receiver at 100% intensity. But if there is a defect, a tiny bubble, a seed, the light scatters. It refracts. The receiver detects a drop in voltage or a spike. The computer logs the event. X coordinate 1,200 millimeters. Y coordinate 4,500 millimeters. Size 0.2 millimeters. Type inclusion. We categorize the enemies. First, the seed. This is a gas bubble, trapped air, or unfined sulfate. It looks like a tiny silver sphere, frozen forever in the glass. Second, the stone. This is a solid particle, a piece of the furnace brick that broke off, or a grain of sand that refused to melt. Stones are dangerous. They have a different thermal expansion coefficient than the glass. They create a stress halo, a tension field. If we let a stone pass, the glass might explode in the warehouse. Third, the ream, or the cord. This is an optical distortion, a streak of glass with a slightly different density. It acts like a lens. If you looked through it, the world would ripple, like looking through heat haze. The laser measures the optical power in diopters. If the ripple is strong, the glass is rejected. If the ripple is faint, the glass is downgraded. Automotive quality, architectural quality, mirror quality. The computer builds a map, a virtual map of the moving sheet. It knows exactly where every speck of dust is located, and it decides the fate of the sheet. We move forward to the cutting bridge. This is where physics meets geometry. The glass is moving forward, but we need to cut it straight across. If we moved the cutter straight across, the line would be diagonal because the glass is moving. So the bridge is angled, or the cutter travels diagonally. Vector addition. The forward velocity of the glass plus the lateral velocity of the cutter equals a perfectly perpendicular line. The cutter does not cut. Glass cannot be cut. It must be fractured. The tool is a small wheel made of tungsten carbide or polycrystalline diamond. It is sharp, but not like a knife. The angle is obtuse, 135 degrees. The wheel descends. It presses onto the surface. Pressure, 2 kilograms. It rolls across the glass. Listen to the sound. Scritch. A high-pitched scratch. It is barely audible. This is not a cut. It is a score, a vent. The wheel forces the glass open just deep enough to create a median crack, a microscopic fissure, 100 microns deep. The surface is compromised. The tension is released. We have told the glass where to break. First, the longitudinal cuts. These are the slitters. They run constantly, removing the edges, the knurl marks. Remember the top rollers, the teeth marks on the edge of the ribbon. We cannot sell that. It is scarred, thick, ugly. The slitters score 2 lines, one on the left, one on the right, separating the good glass from the bad edge. Then the cross-cut. The bridge flies across, zip, scoring the width, defining the length of the sheet. 6 meters, 3 meters, whatever the order requires. Now, the snap. The glass is scored, but it is still one piece. It flows over, the snapping roll. This is a roller that is slightly lifted, just a few millimeters higher than the others. The glass rises over the bump. Gravity pulls the edges down. The score line passes over the peak. Tension. The crack propagates instantaneously at the speed of sound in glass, 5,000 meters per second. Pop, a dull thud. The sheet separates. It is now a plate, a light, L-I-T-E. The edges, the trim, fall away. They drop down a chute, crash, tinkle. They fall into a crusher. Hammer mills spin, grinding the edge trim back into dust, back into colored. A conveyor belt runs underneath the floor, carrying the broken glass all the way back to the batch house, to chapter 1, to be melted again. The circle is complete, but the good plate continues. It accelerates. The rollers here spin faster. We need to create a gap, separation, so the scanners can check the edges. The computer checks the ID, plate number 492, defect map clean, destination stacker 1, plate number 493, defect map stone detected, destination the reject pit. The reject pit is a sad place. It is a gap in the floor. The rollers retract, or a hatch opens. The defective plate dives, nose first, into the crusher. An entire sheet of perfect glass, ruined by a single speck of dust, destroyed, recycled. The efficiency of the line is measured here. Yield 80%, 90%. We strive for 95. The good plates reach the end. The stacking robots, massive hydraulic arms, or gantry cranes, they wait patiently. The plate arrives. The robot descends, a grid of suction cups, vacuum on. Whoosh! The cups grip the glass. The arm lifts, tilts, vertical. We never stack glass horizontally. If we did, the air would get trapped between the sheets. They would stick together, vacuum bonding, and the weight would crush the bottom sheet. So we stack vertically, like books on a shelf. The robot places the sheet onto the rack. An A-frame or an L-buck. Before it lets go, it sprays a powder, lucite beads, or coconut shell flour, or adipic acid, interleaving powder. This powder creates a microscopic air gap. It prevents the glass sheets from scratching each other. It allows them to be separated later. The robot releases, vacuum off. The arm retreats, waiting for the next one, and the next one. Every 4 seconds, a new sheet. 6 meters by 3 meters, 3 tons per pack, 20 tons per rack, 600 tons per day. The forklift arrives. It lifts the rack. It drives away into the warehouse, into the dark, quiet rows of inventory, waiting to be a window, waiting to be a mirror, waiting to be invisible. We have journeyed from the dust to the fire, to the liquid tin, to the cooling tunnel. Chapter 8, ASTM Standards and Defects. The glass is stacked. The glass is cold. But is it good? In the world of industry, good is not an opinion. Good is a specification. We end our journey not with the material, but with the document, the rule book, ASTM, American Society for Testing and Materials, designation C 1036-21. Standard specification for flat glass. This document covers the quality requirements for cut sizes of flat, transparent, clear glass. Classification. Type 1. Transparent flat glass. Class 1. Clear. Quality Q3. Glazing Select. This is the standard for architectural openings, windows, doors, storefronts. To inspect the glass, we must set the stage. Section 7.1. Inspection conditions. The glass shall be placed in a vertical position. The illumination shall be daylight or cool white fluorescent, providing an illuminance of not less than 1000 lux, but not more than 2000 lux. The background shall be uniform, grey, matte finish. The inspector shall stand at a distance of 3 meters, 10 feet. The viewing angle shall be 90 degrees to the surface. The inspector shall scan the glass for a period of time, not exceeding 20 seconds. If a defect is visible at 3 meters, it is a defect. If a defect is invisible at 3 meters, but visible at 1 meter, it is not a defect. It is acceptable. It does not exist in the eyes of the standard. Terminology. Section 3. Blemish. An imperfection in the body or on the surface of the glass. We divide them into 2 categories. Category 1. Linear blemishes, scratches, rubs, digs, faint hairline markings. Table 1. Allowable linear blemishes for Q3 quality. For a light scratch, less than 75 millimeters long, allowed, unlimited. For a medium scratch, less than 75 millimeters long, allowed, but heavily concentrated areas are not allowed. For a heavy scratch, not allowed. A heavy scratch is defined as a scratch that can be felt with the fingernail. We pause to test. We run a fingernail across the cold surface. Click. If it clicks, it is a reject. If it glides, it is a pass. Category 2. Point blemishes, knots, dirt, stones, gaseous inclusions, seeds, bubbles. Table 2. Allowable point blemishes for 6 millimeter glass. Defect size less than 0.5 millimeters. Allowed. Defect size 0.5 to 1.0 millimeters. Allowed. if separated by at least 600 millimeters, 24 inches, defect size 1.0 to 2.0 millimeters, allowed, maximum 2 per lead. Defect size greater than 2.0 millimeters, not allowed, rejected, crush. The standard is absolute. There is no negotiation. A bubble of 2.1 millimeters condemns the sheet. A bubble of 1.9 millimeters saves it. Such is the precision of C-1036. We check for distortion. Roll wave. Remember the rollers in the Lehr. If the glass was slightly soft, the rollers leave a wave, a subtle optical ripple. We measure this with a zebra board, a screen painted with diagonal black and white stripes. We look through the glass at the stripes. If the stripes are straight, the glass is flat. If the stripes wiggle, the glass has roll wave. We measure the optical power in millidiopters. For architectural glass, the limit is often 0.07 diopters. Anything more, and the reflection of a building will look like a funhouse mirror. Architects do not like funhouse mirrors. Finally, we check the geometry. Squareness. We measure the diagonals. Corner A to corner C, corner B to corner D. The difference between the two measurements shall not exceed 3 millimeters. If it exceeds this, the glass is a rhombus, not a rectangle. It will not fit into the frame. It will not fit into the window. It will not fit into the world. We close the book. We close the standard. The inspection is complete. The glass passes. It is clear. It is flat. It is strong. It is chemically durable. It started as a grain of sand on a beach or a rock in a quarry. It traveled through the batch house, through the silo, through the fire of the regenerator, through the liquid tin of the bath, through the slow time of the Lehr, and under the red eye of the laser. Now it sits in the dark, waiting, quiet, still, just like you. The process is over. The noise is gone. There is nothing left to melt, nothing left to measure, nothing left to do. Sleep well. This has been a production of the 8D Sleep